Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks for coming, everyone. It's my pleasure to introduce Crystal Sauer. Crystal is a second-year graduate student from UC Berkeley, and she's been working with Dave Patterson, Armando Fox, Michael Jordan. So she's interested in understanding interesting problems in the data center domain, and she wants to bring in her angle of statistical machine learning to the rescue. So without further ado, take it away.
Thanks, Kashi. So thank you very much for coming. I really appreciate you guys and spending your time. And I'd like to present this work that I've been doing with a few grad students in the Rad Lab, as well as my advisors. And this is a work in progress, so I want to speak with you guys about some ideas we've had in formulating the framework, some kind of interesting observations we've made thus far, and also our plan to go forward. And then I'd be very interested in hearing your feedback. So just to give you a quick intro to our Rad Lab vision, what we'd like to do is have a kind of a portfolio of technologies that will enable a single person at the Elvis level of software development ability rather than Einstein to deploy the next data center application in a weekend, right? So one person, if they have a great idea about a new web service, they could just sit down and code up their idea without having to worry about all the complicated distributed systems problems that go along with that. So that consists of a scalable storage solution, SCADs, as well as an instrumentation and log collection. Also a director operating system that will kind of make decisions about adding and removing machines based on the load. And also my contribution here is to try to observe data from applications and create models that can be used to make decisions about operations issues going forward. So the motivation here is that we're very interested in Web 2.0 applications today. They're very attractive because of some features like allowing users more capabilities than they had with Web 1.0 applications. So instead of just being served a set of customized static content, now these users can interact with each other via posting content and also just keeping in touch with other people in their communities. So these additional aspects make Web 2.0 applications more interesting, but they also make the workloads more challenging to characterize and understand. So this is the primary motivation here. Another motivation is that what we'd really like to do is not just understand the current workload, but kind of be able to predict what would happen to the system due to changes in the workload. So one example that I was made aware of through a conversation with an engineer at Facebook is that they'd like to know, suppose we promote an aspect of our service, such as video. What would happen to the behavior of the system as a whole due to that change? So these sorts of questions are of interest. Also, it's not enough usually just to know the performance that would be resulting from this change in workload. We'd also like to know what would happen to the resource utilization, because we might like to say, okay, I noticed that my response time is really getting larger due to this different workload. Why is that? Oh, it's because various resources throughout my system are being taxed. So several issues here that are kind of leading us to look at this problem. So here what we're doing is, what we have in the normal case is we have workload being input to the Web 2.0 application, and we observe some behavior from that. So what we'd like to do is bring in machine learning to link the workload description with the behavior that's actually observed. And we can use this model to understand the workload that we have already input to the system, as well as to kind of forecast what would happen to changes. So I'm going to go through the application that we're using for some of our experiments and just talk through what logs we're collecting from each tier of the application. So this, what we've used is this Web 2.0 benchmark application that some folks in the Rad Lab are developing called Cloudstone. It's a calendar-based social network application, and when we do experiments with it, we use it on EC2. So first it has a workload generator that is Markovian, so it goes through a series of different tasks, such as user adding an event or searching for an event based on a tag, and each event is depending on the previous event. And this table shows our different request types that are possible. So then on the other side of the system boundary, we have the front end, which consists of the Nginx reverse proxy and the HA proxy load balancer, and this is the appearance of the application that's set forth. So from the Nginx machine, we collect the performance monitors. This is supposed to have a label here, but this is from IOStat, NetStat, and VMstat. So we just we have a daemon that runs on these machines, and every 1 second it will just dump the current state of the machine. So similarly for the HA proxy machine, we have the HA proxy log, that's the top one, which gives us a rich source of information of request-based features, such as what type the request is, which we can extract from the URI. Also, the response time observed by that request and its return code. And then again, we extract the IOStat, VMstat, and NetStat. So similarly for the Rails machine, again, have the monitors, but we also take the Rails log. And so the Rails log also serves as a rich source of information about the requests. So from the Rails log, we're able to collect features such as like the queries that are executed from that request and the tables and columns that they touch. And then we also collect the performance monitors from the storage tier. So I just wanted to show you some observations of the variability that we actually observe within the requests. Because it's an interesting thing about Web 2.0 is that some of the prediction techniques that worked well for Web 1.0 have been shown to break down for Web 2.0. So just knowing the request type isn't enough to reliably understand what will happen with the workload at that time, just because there's more variability. So what we show here is these are the 14 types of requests that we observe with Cloudstone. And you see that, so for like request 1, 10, and 12, these are very simple. And so we see a very peaked distribution of the response time observed by those requests. But for the other requests, it's a much broader distribution. So we really don't know what the response time will be. Sorry, go ahead.
So in these results, what are you assuming about the sort of background load? So in other words, if I just look at request 9, for example, so are you only putting request 9s into the system, or is there some stationary background workload that's taking place?
Yeah, so no, this is just like we have a 10-user workload generator going on, and so this is like request 9 observed with other requests in the system. And so that's I'm glad you brought that up, because another factor that contributes to the variety of response time here is that we have these requests observed in the context of other requests at the same time. So, and that's always the case in web applications. We never have just a single request being input to the system. It's always observed concurrently with other requests. So just knowing the request type is not going to give us enough information, even though that worked previously. Yeah.
So other requests, do you mean other requests issued by the same user, or are there concurrent users using that?
Yeah, there's concurrent users. There's the fixed like 10-user load going on. Yeah. Okay, so and just to zoom in on one of the request types, we have again just the distribution shown here.
So why do you say that this is different from Web 1.0 workloads?
Well, so I had observed this paper where they analyzed some of the Web 1.0 applications, such as Rubus and some of the other, I think, spec web benchmarks, and they had shown that some of the techniques worked really well for predicting the response times and other resource utilization in that case. But because of in the Web 2.0 setting, those really broke down, and it was just because of the additional complexity in the workloads there. I can give you a pointer to that work if you'd like. Okay, so now that I've gone through where we're actually obtaining the logs from, I'd like to present how we develop the input representation. So the workload that goes to the system is a stream of requests. And here by the color of the squiggle, I mean to indicate the request type. So what we do is instead of considering a single request, we consider an interval of 1 second. And so the reason we chose 1 second is that the response times all seem to fall well below 1 second. And so we figured that most requests would be completely captured during that interval, and the ones that overlapped would probably be having a negligible contribution to the load in that interval. So then at the end of each interval, we match up that interval with the measurements of resource utilization that we obtained throughout the system. And we also create this bag of words representation of the request types that are happening with each interval. And so you can see that the colors of the bars indicate the request type, and then the heights of the bars indicate how many of those requests we saw within each interval. So, and the reason I'm kind of labeling this as X and Y is we separate the features that we can observe before running the workload and then after running the workload. So things about what request types are happening during that interval don't require actually running the workload. But then information about what the resource utilization is will, of course, require that. And in addition to just the distribution over request type in the X, we also put some of the request-specific features that we obtain from the Rails logs, such as the queries that will be generated from each request type. And we can obtain that information also without running. So just to reiterate, the X is features that we can observe before, and Y is features that we can observe after. And so what we're doing here is really laying a foundation for prediction. And the reason we want to separate the requests into these X and Y is because when we're asking questions of the model and we're trying to make predictions, we'd only have the X features available, right? So it makes sense to cleanly separate those, and then we can kind of make predictions about what the Y would be. So prediction really relies on the fact that you can find things that were similar in your training data set toward this example.
So are you assuming that the request generation is independent of the response from the server?
I think it's a closed loop workload generator. So there's like some think time after they receive the return from the server.
So then how does that, I mean, you talked about separating the pre-observed features and the post-observed features, right? But it seems that if the requests are generated based on the responses, the separation doesn't really vary much.
But like I guess what's happening during each interval is kind of like, you can isolate that, right? Because you know that there's just certain requests going in, and then like those are observing some sort of response from the system, right? But like when you actually want to make a query of the system, like you could just present like, okay, there's this X. I have this workload that I want to ask a question about. You don't want to have any of the resource utilization features kind of mixed in with that, because that would kind of muddle the query of the system.
Well, I don't know that this is the same question you're asking, but one question is that sometimes I ask a query, let's say, and then I get some results. And the next question I ask depends on what I got back. For example, how many tokens came out of that might depend on that. Do you have any such requests, or they're all independently generated, irrespective of the actual output of that particular? I think that was my way of.
So it seems like maybe what you're saying is kind of the dependence between consecutive intervals. Yeah, I mean that's definitely true. Consecutive intervals depend on kind of what happened in the previous.
The intervals.
You're assuming. Are you assuming a stationarity? The distribution of all requests is stationary. So effectively, over time, you're seeing the set of all requests that are common. And it's not like there's some trajectory. The requests just go off and they're perpetually changing, never return.
Mm-hmm. Yeah, I mean, the requests are always drawn from the same distribution. That could be changed, but we haven't done that for this setup.
Or like what happens if like one of those messages gets dropped, there's no, so that I guess is bordering around the question that was asked. So if I don't get the response back in time, that delays the sending of the new request without even changing the semantics of the request itself.
Okay, so I think just the way we handle that is that we are kind of like, for a query, you'd be just asking about a single interval. So you're kind of not really thinking too much about what was happening before. You'd just say, for this new workload at this time, what would my performance be, right? So, I mean, one thing we've thought about is what interval makes sense, right? I mean, we chose 1 second here just because it seemed like most of the requests were falling within that, but definitely I'd be open to see, like, if someone were really analyzing their system to look at this, what interval would be more attractive to kind of like mitigate the effects of, I guess, things that happened from previous requests. Okay, so as we're looking to actually do prediction, this really requires that we can find similar examples to our queries in our training set. So one approach that that can be done is to take the k nearest neighbors within the training set and then average their resource utilizations and then return that as the prediction. So questions that k nearest neighbors is a very well-known technique. It's very well used throughout many domains such as object recognition, every time there's a classification task, that seems to be one of the simplest approaches. So questions that are involved is what should k be? And so usually the way that we do this is we kind of look at our accuracy and see how that kind of improves with k in order to find an empirical determination of what k should be. So it's sometimes the case that we see, okay, once I hit a certain value of k, I don't gain much by adding more neighbors after that. So that's what we've done here. Also, there's this idea of what space should we really be looking at here when we're trying to find similar neighbors? Should we be looking at just the raw data, or should we try some transformation on that raw data to look at a different space? So what I want to show here is that the raw space is not appropriate for this comparison. So I have a training set of 1,000 points. And so I looked at a random point 500 within that set. And what I'm showing here is its projection onto 3 of the different resources that we're looking at. So these orange points are the resource utilizations of its most similar points with respect to the X view. Okay, so if we just looked at what workloads were most similar, these were the resource utilizations of its nearest neighbors. However, these were the most similar resource utilizations of the points in the set. So just because 2 workloads looked similar, that's not necessarily a case that they might have similar resource utilization. And so we take from this that the raw space really isn't the appropriate place to look for k nearest neighbors to do the prediction. So we talked about how we input our requests, we obtain the resource utilization. So now we're going to, and this comprises a 2-view data set. So
wise, is there an aggregate over the 1 second interval, or only at that particular instant in the 1 second, at the end of the 1 second?
Oh yeah, it's an aggregate over the whole interval. Okay, so this X and Y comprises a 2-view data set, and an appropriate algorithm for kind of getting the similarities within 2-view data sets is KCCA, Kernelized Canonical Correlation Analysis. And this was developed, I guess, several years ago by Michael Jordan and one of his grad students at Berkeley. And it's kind of just a twist on a very classical algorithm, canonical correlation analysis. And that produces the data projected to an abstract space that we can use to do the nearest neighbors comparison. So in order to do this, we first kernelize our X and Y views of the data set. And the way that we do that is each input, each point in the X is compared to all other points in the X via a Gaussian kernel. So they're compared like by entry, and then the single value reported as the similarity between those points is just the average of the element-wise similarities. And so then the n by, let's say, d dimensional x, where d is the number of features, is translated via the kernel to an n by n kernel matrix. And that kernel matrix just represents how similar each point is to every other point. So the way the KCCA algorithm works is we take our x and y representations to kernel matrices. Then we solve this generalized eigenvalue problem. And so what these A and B matrices are they're these two sets of eigenvectors that will maximize the correlation between the projections of kx and ky. So it's that I want to project kx onto some vectors and ky onto some vectors, and I want to choose those vectors such that those projections are maximally correlated. So they're really like the dimensions that best capture the correlations between the two kernel matrices. And what I get out is something that's quite similar in both the x and the y. So now I'll just discuss how KCCA can be combined with the k-nearest neighbors approach to finding similar requests. So here we have in the top box our raw data, our x and our y. And we have in the bottom box our projections of the raw data into onto the dimensions of correlation. So here's a new point in the red star. And we want to try to predict its y vector. So we project it onto the dimensions of correlation, and we find its 3 nearest neighbors. Now, because we know that there's such a similarity between the two views, we know that those 3 nearest neighbors will be the same in the ky times b view. And we can hypothesize that the point would be at the same coordinates in both views, because that's because of the correlation between them. So the reverse mapping from the ky times b space is not really a deterministic problem, because we've kind of lost a lot of information by reducing the dimensionality onto these dimensions of correlation. So what we do, we employ these nearest neighbors, and we look up their positions in the raw data. So we already know what their raw data vectors are for the y. And then we return the average of those for the prediction for the resource utilization of the query point. So one of my colleagues with whom I'm working on this project has done a couple of case studies using this approach to prediction for some other domains. So one of her case studies was multiple metric prediction for queries to a parallel database. And she's presented this just a month ago at ICDE. And she was able to outperform the query optimizers in predicting the cost of each query.
So for this one, how did they choose the interval? And for example, the 2.0, you said most requests are known to be within a second. Mm-hmm. I assume you don't have such a easy measure for database queries, right? Do you know how they chose that interval? So
here it was a little, I think it was kind of clear what to choose, because they just treated each query actually separately. So each query had, as its x, it was the query plan compressed into, I guess, an array rather than in the tree. And then the y was just the various metrics that they wanted to predict. But so even though it was a parallel database, each query was run independently. Yeah, so that's kind of a difference between the two settings. But yeah, I mean, that's a good point that in this setting, she was looking at quite a broad range in running times of the queries, so it would be hard to choose an interval that would be appropriate. So also she looked at a case study of finding the best configurations for running scientific codes on multi-core. And again, she was able to outperform some of the other approaches that are usually done for auto-tuning, and even come within 1% of an expert-tuned optimization for these scientific codes. So this approach and the similarity that it gives has really been shown to be quite applicable to the prediction problem. So what I wanted to show here, following up on the nearest neighbors experiment from before, where we saw that just looking at the nearest neighbors in the raw data wasn't really going to help us. What I've shown here is that if I take that same 0.500 and look at its nearest neighbors in the projection of the x and the projection of the y, they're the same in both the kx times a view and the ky times b view. So this really gives us a good foundation for the prediction, because a single workload will be able to find similarly behaving workloads, because the similarity in this KCCA space takes into account both the workload and the resource utilization of that workload. So I'm still working on kind of getting the prediction going. So I'll have some results on that soon. But just wanted to show like kind of our problem formulation and some of the motivation for the approach, and get some feedback there. So yeah, we're very interested in looking at Web 2.0 because of the additional complexities that it brings. And we really believe that KCCA is quite applicable across many domains and many different types of systems. And it's because it gives us this notion of locality that deals with not only the input, but also the resource utilization that's actually observed. So some of the things I'm going to be doing in the near future is looking at what kind of additional features could I include in the X view that would help me with the prediction. Also, what's the best interval length? And of course, I'm sure that it'd be much more interesting to have more app servers and database servers, so I'll be adding those. So some things that I'd especially like feedback on are what are some other features that would be good to include. Also, so I mean, I mentioned that I'm collecting these resource utilization monitors from all the machines, and each one has tons of entries. So I have many metrics to choose from, but I'm curious about what would be the most of interest. Also, what would this kind of model be useful for? Like, what kind of questions would you like to be able to ask? And it seems like some of the concern with this approach is that it lacks interpretability, right? When we look at the model, we don't necessarily know why those were the neighbors. And so I'm wondering, like, what could be kind of put on top of that to make it more clear what we're actually presenting. So yeah, I'd just like to invite your feedback as well as any other questions. Thank you.
I mean, have you tried making predictions of just simplest forms like, okay, so here's the performance I was getting, resource consumption I was getting with one workload. Now I'm going to double the number of servers. What happens to the resource requirements? Would you expect it to work on that kind of problem, or? So if we wanted to do that, we'd have to include the number of servers or the configuration of the system in the feature vector. Right. So we haven't done that thus far, but we could definitely try doing that. Okay, if you do that, then you're expecting KCCA is going to it basically sort of has to learn what the workload response curve is. Basically, is resource usage linear in the number of servers, or inversely linear in the number of servers, inversely quadratic, right? I mean, yeah. Is that something KCCA can do, or is that? So no, I think in general prediction is more of like, okay, how can I find something similar in what I've already observed to what I can now, what I'm being asked about. So I think I think the main challenge here is kind of the ability to extrapolate, right? Because I think in many kind of prediction tasks, we're asking about things that are similar to what we've already seen. But in this case, it seems like what we really want to ask about are situations that are quite different from what we've already seen, right? And like, yeah, we want to ask questions about scaling up. So no, I mean, this is mostly for learning like patterns that are already kind of present in what we've observed. So yeah, I've definitely been thinking about that a lot. How can we hope to extrapolate to a new configuration?
So that was kind of the flavor of my question as well. So it seems that one of the things that you motivated this work by at the beginning was Facebook comes to you and they say, what would happen if we added this new service? What's our resource utilization going to look like, right? And it seems like for that type of scenario, what your clustering technique will say is that you'll have the input vector, and it'll map to some part of the space that there's nothing around there. And so you basically wouldn't be able to say anything about that. And so I guess what I'm wondering is, have you thought more about maybe like hidden Markov models or things like that, so things where maybe there's some intuition about some hidden state of the service that would allow you to extrapolate to these unknown scenarios.
So something I actually have been thinking about that's kind of related to that is maybe bringing a prior to populate the space more, right? Because I think the problem that we have now is that the KCCA space is not sufficiently populated to ask questions about things that we haven't seen. But I think it could be possible to bring in like a particle mass prior, like a Dirichlet process that would give more density throughout the space, and then that could possibly be used for asking questions about what we haven't seen. So I think that would be one step toward that, but then a problem there would be that you'd have only the prior contributing to wherever in the space that there aren't points from the observations, right? So I think it'd be interesting to see, okay, could we bring the observations to impact the prior enough so that even in this points where we don't have observation mass, could the prior mass be kind of conditioned to be more accurate?
Another question I had too was a result of things like load spikes or things like this, which you might expect to be fairly rare, but when they do happen, you care a lot about are your models correct in this regime, or can you at least over provision these scenarios. And so I wonder if you've thought any about that. I mean, so you talked a little bit about the Gaussian kernels and things like this. I have to admit, I'm not an expert in Gaussian kernels, but whenever I hear things like Gaussian, I think, well, you're actually encoding some assumption about the incidence of rare things, for instance, right? And that's going to affect how you sort of make your later predictions. And I was wondering if you looked at, let's say, the actual distribution of things like these crazy load spikes and how your technique would handle things like that. Because what if, for example, you only have one data point for some load spike, but you really want to be able to handle that if that ever happens again. So it seems like in your technique what would happen is that you would, if I give you a similar vector, a similar set of x's, you map that point into the projected space. You'll find one point that's very similar, and then maybe k minus one others that don't really help you that much in terms of predictors. Is that correct?
Yeah, so that's a good point. Yeah, I think what we could do is we could kind of just report that number of like maybe the distribution over similarities between the query point and the k nearest neighbors, right? So if we see there's one very strong similarity and then a lot of really poor similarities, then we know, we're probably in a very unpopulated region of the space. And so we should more highly weight things that are very similar to our query and, really kind of filter out the impact of those others. So I think in the database work that my colleague did, that situation was, I think, simpler than this because she had seen both short and long-running queries. So I guess she had seen pretty much everything that she would want to answer, right? It was just kind of a new query that was, it had different parameters, but it was still either short or long-running, and so there was enough information there. So she just took the 3 nearest neighbors and took a flat average of their parameters. So, but it seems like in this case, maybe where we may not have seen enough instances of the rare cases, maybe more like a weighted average is more appropriate for computing the predicted response time.
So I think the general stream of questions is that, do we try to make KCCA work for the problem that we're looking at, or do we want to question what techniques we want to bring to the table? And I think one thing that can help is if we have a list of these are the what-if scenarios that really people like Facebook would care about. And then you work backwards from there to understand what features need to be incorporated into the model.
Sure.
And then let's worry about what solutions need to come up.
Sure. Yeah, and that's what we've definitely been very interested in, collecting that sort of information, because we don't really know what are the most pressing what-if questions.
Like this goes back to some of the responsiveness, right? So for example, does Facebook really wants to know whether my data center is located in one location and it's a geographically distributed client, what happens to the response time? Like nothing really changes in my infrastructure. It's just the client population changing. I did not tweak my application at all. Are those the set of questions you want to answer? Which one takes priority? And the kind of questions you were asking, whether there's a sudden load spike. So all those things, you could see how you could optimize for answering each of those individual questions, but then the set of questions that you want to answer, that fundamentally dictates what techniques you want to bring in.
In particular, I think the nonlinearities are some of the most interesting points that may require fundamentally different modeling techniques. And so, like I said, I'm not an expert in this, like the Gaussian kernel stuff, but I mean, if you just look like the financial market right now, one reason why, basically we're burning tires for warmth is because they had all these economic models that are based on these Gaussian distributions for things like volatility. And you actually have these fat-tailed distributions, right? And so I think there's sort of like one large set of questions, which is sort of what does my average case behavior look like, or what will things look like in the normal case? There's another set of questions that says, what if I'm under attack because there's all of a sudden this very popular content that's uploaded, and how am I going to scale out in that situation? And I think dealing with that second set of questions may require totally, different approaches towards things. I mean, maybe it's going to require some machine model, some crude machine model of how, I don't know. But it just seems like two basic classes of things you might want to look at.
Okay, so if I understand what your comment is you're saying that the queries that we're really going to be interested in are the corner cases that we may not have seen in our training set, right? So that might really not be enough to answer those questions.
Yes, I don't work with Facebook, so I don't know, but I'm just saying that, in other words, there's a set of things for which clustering around things that look similar to what we're looking at is useful. There's a class of things for which that isn't as useful. And I think it's some of these, abnormal spikes or, 4 sigma events whereby you might want to start thinking about, somewhat different models.
Yeah, that's a really good point. But I think one thing I would say about, I guess, your comments about the Gaussian kernel is that, often a Gaussian distributional assumption is made about things, and that's where we can fall into these problems with, the very light tails. But in our case, like using the Gaussian kernel, we're not like making a distributional assumption about something. We're just kind of smoothing the similarities values to make them kind of fall within 0 and 1 and kind of be like, more interested in things that are kind of centered around, that are very similar and less interested in things that are less similar, right? So we're, that only impacts the values that are given to the similarities between 2 points. We're not saying that things are generated from a Gaussian distribution. So I think that's where we'd probably fall into more problems with that assumption.
Okay, so basically it's like a shaping function for the...
But I still think your point is very valid about the corner cases are kind of, in the parts of the space that are not populated.
How do you pick the sigma for that smoothing function?
I think we're probably just using like a 0, mean, 1 sigma kernel. But, I mean, we could... Yeah, I mean, that would definitely impact, like, I guess, the actual values for the similarity. But I think probably you'd still find the same points as being the most similar to a query.
So like if you vary that sigma, do you still see the basic clustering properties, or do they change radically in responses?
Thank you.
Great, thank you.